The next part's on continuity and differentiability. So as we saw in Chapter 2, if the limit of a function exists everywhere, then the function is continuous. This has some implications for the derivative. If f is differentiable, that means that its limit exists, and therefore it means it is continuous. So differentiability implies continuity. Differentiable implies continuous. Conversely, if a function is not continuous, it is also not differentiable at that point. So at any place the original function is not continuous, the derivative also won't exist because its domain is smaller or equal to the original. Okay. Mathematical theorems often follow the if-then. They do not work in reverse unless specified. So for this theorem, what do vertical tangent lines mean for differentiability? So in this particular graph, this function is continuous, but it has a vertical tangent right there. It means that it's not going to be differentiable. So a vertical tangent line means not differentiable. Okay, at C, wherever C has a vertical tangent, right? Okay, and that can happen at a point where the function is continuous. That's one way to shrink the domain of the derivative versus the domain of the original. All right, continuing on, the next page here, we have some functions here, and we want to talk about the derivative at, specifically, x equals 3 for all of these. All something different going on at x equals 3. So in the first picture, at x equals 3, the tangent seems to be horizontal. So we can say that f prime of 3 will exist and be 0 because you have slope or the derivative 0 at x equals 3, this point right here. That's one thing we can say about that one's derivative. For the next one, there's a vertical asymptote at 3, so the original function doesn't exist at 3. So it's also true that g prime of 3 will not exist or be undefined. The derivative at 3 is undefined. It's also true in this case that g of 3 is undefined. Usually in terms of limits, we say doesn't exist because the derivative, remember, is a limit. We usually say doesn't exist instead of undefined for limits. But undefined would be okay in this context if you chose to use that word instead. Okay. In h of x, again at 3, in this case, we have a tangent that would be vertical. So even though this function is continuous, the derivative at 3 doesn't exist. Okay? And again, if we want to write the reason for that, it's because there would be a vertical asymptote in the h of prime of x function at x equals 3. You don't see a vertical asymptote in the h of x function, but there is one in the h prime of x function. It goes vertical there. Part D, we're looking at another graph here where at 3 you have two different values that you're approaching, and so the derivative won't exist here either. So there are, again, anytime that there's a discontinuity in the original function, let's see, the derivative won't exist at that point either. Okay. Letter E, we're looking at the r of x function. And the r of x function, the derivative is a negative value and a positive value, and you can't get between those two in one value. It's not 0, it's a jump function. So it's sharp. So r prime of 3 also will not exist. And then in letter F, if a value is excluded from the domain of the original function, it's certainly just excluded from the domain of the derivative. So s prime of 3 also fails to exist, this time because it's not in the domain of the original. So s of 3 is undefined. So you certainly cannot have a value of the derivative because the domain of the derivative is a subset of the domain of the original function. Okay. Questions to ponder. Can you have a function be continuous at a value c but not differentiable? Yeah, we saw that on the previous page. A function can be continuous in a variety of ways at a value c. One is in the sharp point, right? It's continuous there but not differentiable. And another way is it can be continuous but have a vertical tangent. So that's another way that it can be continuous at a point but not differentiable. Can you have a function be differentiable but not continuous? And this is going to be no. That theorem said that differentiability implied continuity, and that's because differentiability means that the limit exists. It also means that the function value exists. And it also means that they're equal. So therefore, differentiability implies continuity. So in order for a function to have a derivative, it must be continuous, but just because it's continuous does not guarantee it has a derivative. When is the function not differentiable at a point? If a function is not continuous at a, then it's not differentiable. Not continuous implies not differentiable. If the graph of f shows an abrupt change, a sharp point or a sharp corner, like we saw, a sharp change, it's not differentiable. And again, a vertical tangent. And a vertical tangent could be two forms. It could actually be an asymptote. That could be a vertical tangent. Or it could be super steep in the center. That could be a vertical tangent as well. So many cases where the function is not differentiable at a point.